2 and gamma 3. So we put 5 divided by 6 and minus this part, 1 divided by eigenvalue. And we can see that only the first gamma has positive value, and these two are negative. So we switch off them, and we have this power allocation scheme, which is equal to only one value in first position, and it is equal to 3 in this case. So next, let's continue this task. I will start it with new page, and now we need to, let me check. So we need to calculate closed loop capacity. In this case, we will use water pouring algorithm. So we have
allocation.
Yes.
This means so that first channel.
Yes, we will.
Send the signal.
Yes, only from one channel, because we have this signal to noise ratio very low in this case. So in low cases, it is better to use only one data stream. If we have good SNR, so high SNR regime, we can use all data streams and with equal power allocation.
The number, what says?
Why this one is free?
Yeah.
Because the sum by this diagonal should be equal to MT, number of transmit antennas in this case.
It should be equal to MT, or it should be equal to like a total power of a transmitter? Like
no, in this case only MT.
Like if we have, in this case, we have a total power is 1 watt.
Yes, but
if we have a different power, like total power have like 5 watt.
Yes, but it is something like normalization by antennas. So it is empty. So I can say that this one should be equal to empty. But about power, we will scale it in the main equation, because if you remember, when we write the received signals, we write as well. So y is equal to first the scale factor, then channel, and then transmitted data plus the noise. But in this case, this S is equal to something like first our recording. No, in this case we let's write only with power allocation scheme. So can we use power allocation scheme? No. Yes. So first we need always write this precoding times this power allocation matrix, but the square root of this matrix, and times send data. So yes, this D is equal to MT, but we will use the square root of this D in this case.
So, for example, if instead of 3, we have another number, 6, for example. What is that?
It is only if we have number of transmit antennas equal to 6.
So this is only.
Yes. So it is how we allocate this power to antennas. So for example, if we have good 2 channels, for example, and maybe first one is better, we can say, and maybe let's write like an example here. For example, we have number of transmit antennas equal to 2. Both channels are good, but first one is better. And for example, for first one, we say that this power allocation scheme give 1.5. So the second one should be equal to 0.5, because the sum of these values should be equal to 2 in this case, to the number of transmit antennas. And maybe you can say why we need this thing. because if we look to this equation, and let's use the same value here, so we can say that we transmit only one data stream. So in this case, this signal S is equal to this matrix with precoding times square root of 3, let's say, and times D. So this thing is square root of MT, we can say. And if we put this thing into this general equation, you will see that, let me write it as square root of P and square root of MT. So channel H. And of course, from the right side, I should use the multiplication by linear equalization, but let's assume that this one before this linear equalization scheme. Then we multiply it with by square root of MT times this data stream plus noise. And you can see this one and this one is eliminated, I can say, and we'll have this only the scaling of power. So that's why this power allocation matrix in the main diagonal should be equal to MT. This is the main thing here. So it is only the right normalization of full equation. So yes, and we have this data stream plus noise. So let's continue this task. I will use another paper. You can continue in your textbooks as follows. So this is practice 3. Practice number 3. So today is the first day of summer. That's great. It is summer weather outside. Yes, it is not so cold as 1 week before, I can say. So sorry. So let's write continue, in this case, task 2. So continue task 2. We will look to the subtask C here, subtask C, and we need to calculate. Let me see what we have here. So we assume not the closed loop capacity, but the water pouring algorithm as well. Okay, I see it. So here we assume this water pouring algorithm. Water pouring algorithm. And first, we set our iteration counter to 1. So P is equal to 1. First, let's calculate our water available mu. And maybe I will use first general notation for this one. So MT divided by, let me see it. Not MT, I think 1 divided by R should be here. Yeah, I will use this algorithm. So for this one, yeah. So 1 divided. We can also move out this empty. Maybe let's write like this one also. It is also right equation. We just move number of transmit antennas outside of braces. So empty plus 1, then 1 divided by rho. So this signal to noise ratio and the sum of our eigenvalues. And let me here introduce to refresh in your mind. So MT is equal to 3 in our case. Then our signal to noise ratio is equal to 0.5. So this one from subtask A, as I remember. Yes, from subtask A, you can see that this signal to noise ratio is equal to 0.5. And then the matrix of eigenvalues is 2, 1, and 1. So let's put these values into our general formula for water level. So mu is equal to here 3 divided by, and also the rank, we can say it from the number of eigenvalues, but the rank is equal to 3. So 3 minus 1 minus 1 here. So it is just 0. Then inside of braces 1 plus 1 divided by 1/2. So it is, we should move this from denominator into the numerator, but let's write the sum of these eigenvalues. So first one, 1 divided by 2, then plus 1 divided by 1 and 1 divided by 1. So let's see what we have here. This thing is equal to 5 divided by 2. Then we multiply it by 2 and sum 1 here. So this thing is equal to 6 inside of the braces. And this thing is equal to 1. So we can say that water level is equal to 6. Next, let's calculate our power allocation values. So first, as well, I will give you the general formula or general equation. So gamma I is equal to mu minus MT divided by rho here, and multiply this one with 1 divided by eigenvalue with index I. So let me move my page here. Let's start with the first one. So gamma 1 is equal to mu 6 minus number of transmit antenna 3 divided by signal to noise ratio, it is 0.5, and times here 1 divided by first eigenvalue, it is 2. So we can say that this one and this one is eliminated here. And now the first gamma is equal to 3. Then let's calculate the second one. 6 minus 3 divided by 1 divided by 2 times 1 divided by 1. And you can see this one is equal to 6 here. And in this case, second gamma is equal to 0. And the third one is also equal to 0 because eigenvalue is equal to 1. And you can see we have the rank equal to 3, but we will use only one data stream. So we reduce like number of data streams equal to 1. Yes, yes. If you see that the first gamma is equal to the maximum value, you can say, oh, of course, the second and third is equal to 0. Yes. No. Or maybe yes. You can say that it is equal to 0, but maybe sometimes it can be less than 0. Yes, -1. So yes, I think it's better to calculate everything. Yes, to check it. And if someone is equal to -1, we also just turn it off.
So we only switch off from 0 and -1.
Yes, it is something like if it is negative, we switch it off. So just put 0 into our power allocation matrix in this index. So you can see that this is the final answer, but you can also write it as this power allocation matrix D is equal to 3, 0, and 0. And of course, you can put also zeros here. But it is maybe enough if you write it as diagonal matrix, like this one, without these additional zeros. And of course, let's write this main constraint for the overall gammas, that the sum of gammas from 1 up to our rank R. So in this case, gamma 1 plus gamma 2 plus gamma 3 should be equal to number of transmit antennas. And we can check it. 3 plus 0 plus 0 is equal to 3. And this one is equal to number of transmit antennas. So this one is correct. So let me check what we should do next. So 1 divided by 2. What we have here for closed loop capacity. Maybe we can leave this closed loop capacity subtask and let's see what we should do with critical scenario. So let's call this one as subtask D for us. So subtask D. I think it is more interesting case because we, for task 1, already calculated this closed loop capacity. You know how to do it. So for this subtask D, the main question here after which critical SNR, after which critical signal to noise ratio, or we can say it as raw crit, as raw critical. We will turn on second and third streams. So we will turn on second and third, maybe streams, or we can say also as eigenmodes. Eigenmodes. So do you have some ideas how to do it? So of course we can start maybe with general formula for, because right now I have no solution here in my textbook, and we can solve it together. So it is also interesting for me. Of course, we can say that water pouring algorithm counter should be only equal to 1, because we need to only calculate it once and leave all data streams switched on. Yes. So we can say that P is equal to 1. Then let's write this water level equation using this P equal to 1. And let's change our raw with raw crit as raw critical. So mu in this case is equal to number of antennas divided by the rank. Inside of the braces we have 1 plus 1 divided by raw critical. And then here the sum of eigenvalues. I from 1 to 3. Lambda I is 1 divided by lambda I. So let's see next. Maybe we can calculate this overall sum here. So it is equal to 1 plus 1 raw crit. And here the sum of 1 divided by 2 plus 1 divided by 1 and plus 1 divided by 1. So it is 5. Oh, sorry. So it is 5 divided by 2. And we can say that our mu should be equal to 1 plus 5 divided by 2. And here also raw critical. So I think this is the first step. Then let's assume this general formula for gammas. What we can see in these gammas. So let's write gamma I should be equal to this mu minus number of transmit antennas divided by raw critical and multiply it 1 divided by lambda I. So next, I think we can write three equations, but let's see. Maybe let's write it in general formula first, in general case. So it is equal to 1 plus 5 divided by 2 raw critical minus 3 divided by rho critical times 1 divided by lambda I. Yeah, I think we can use here inequation. So we can say that this thing should be more than 0. Yes, because we need to turn it on. So this thing is more than 0. So let's see. We can leave rho critical in the left or right side, I think, and lambda I vice versa. If rho critical left side, so lambda should be in right side. Maybe we can write it as 5 divided by 2 rho critical minus, let's here write 6 divided by 2 rho critical times 1 divided by lambda I. Then this one, we can also write 2 rho critical divided by 2 rho critical. So let's write 2 rho critical, 2 rho critical. Or maybe, in this case, we will have it on both sides, yes? But we want only from one side. Interesting case. Okay, maybe let's leave this one as 1. And if we multiply, maybe let me write it by pencil to see it first. If we move this one outside of the braces, what we have here, 5 minus 6, 1 divided by lambda I. What next? What next? What next? So this overall thing should be more than minus 1. Okay. Then we can, yes, maybe we can do it as this thing. So let's write first that this thing, 5 minus 6, 1 I. So we first move minus 1 to the right side. Then multiply both sides by 2 rho critical. So this thing, 5 minus 6, will have something like this, minus 2 rho critical. Then we can multiply both sides by minus 1 to change the sign of this rho critical. So it will be something like, I will write rho critical from the left side in this case. So it is 2 rho critical more than 6, 1 divided by lambda I minus 5, if I'm not mistaken. And then we can divide both sides by 2. So we have rho critical 3 multiplied by 1 divided by lambda I minus, let's write 2.5. And in this case, we can put here, And in this case, we can put here our lambda i's. So I think we can start with the smallest one. So it is 1. So let's assume this lambda 2 and lambda 3, which is equal to 1. In this case, this rho critical should be more than 3 times 1 divided by 1 minus 2.5. And we can say that rho critical is equal to, or should be more than 0.5. Yes? So the critical one, when we turn off our second and third, it is 0.5. But if we increase, for example, 0.1 or 0.6, if this row, for example, let's write only just as row. So if we assume that our row is equal to 0.6, we will turn off the second and third data streams. So we will turn it on. Maybe let's show it as we said. So I think you can do it in more elegant way, but the main thing is here that row critical is equal to 0.5. So if row more than 0.5, we turn our two additional streams. If it is less than or equal to 0.5, we will switch it off. Yeah, great. That's great. Then maybe I will show you some task with multi-user Mimo. But let me check which one will be better. Maybe let's consider the logical task when we have only the signs, like the characters, without the exact values. So without numbers, task without numbers. Let's write this one, task 3. Task 3, multi-user Mimo. So here we consider a multi-user Mimo system where transmitter is a base station. So it is downlink case, which is considered in our lectures. And this base station has the number of transmit antennas equal to 4. So our base station has number of antennas MT equal to 4. And moreover, there are 2 users, and each of them has 2 antennas. So let me write it as users. And for first user, we have number of receive antennas equal to 2. And the second one also has the number of antennas equal to 2. Then it is also given the channel structure for first and second user, and maybe I will rewrite it for you here. So H1, we have the structure with H11 subscript 1. So it means that it is first user. Then H12 subscript 1, H13, superscript 1, h1 4 superscript 1, and same thing, but second row with first index 2. So h21 superscript 1, h22 superscript 1, h23 superscript sorry, yes, superscript 1 here, and h24 superscript 1. The same structure of a channel for the second user, but with superscript 2. So maybe let's write it here also. So h11 superscript 2, h12 superscript 2, h13 superscript 2, h14 superscript 2, and the second row h21 superscript 2, h22 superscript 2, h23 superscript 2, and the last one h24 superscript 2. So channel for the first and the second users. Furthermore, F1 and F2 matrices are the precoding matrices at the base station for user 1 and user 2 are given. So it is only noted as matrices, so F1 and F2, and moreover, decoding matrices also are given by this notation D1 and D2. So maybe let me write that this one and this one precoding matrices for user 1 and 2 respectively, and this one is decoding matrices, or yes, let's write decoding matrices for user 1 and 2. And moreover, you are given by transmitted data and received data for user 1 and user 2 respectively, as I can see it here. So S1, S2 transmitted signal to user 1 and 2. Transmitted signals to user 1 and 2. And the last thing, received signals. So R1 and R2. It is received signals at user. So received signals at user 1 and 2. And here, first subtask is specify the explicit dimensions of the following vectors and matrices. So S1, S2, R1, R2, F1, F2, and G1, G2. So let's write first subtask here. Specify the explicit dimensions. Specify the explicit dimensions. So for S1, S2, R1, R2, F1, F2, and D1, D2. So these all matrices and vectors. So let's open in our textbooks or notebooks the part with multi-user Mimo, and what we can see here. So first, transmitted symbols is equal to the number of data streams. So we can say from our notebooks, SK has the dimension equal to RK. Then what is next? I think we can say that these received signals is equal to the number of receive antennas or less than number of receive antennas. So MRK, it is the main constraint. So it is equal to from 1 up to number of receive antennas at each user. Then if we assume the precoding matrix, what we have? So it is equal to MT times RK. So number of transmit antennas times the number of data streams for user K. And the last one is the linear decoding matrix or linear equalization matrix. DK is of size RK times the number of receive antennas. And now we can, using these general, not equations, but maybe general notation, we can specify the dimensions of S1, S2, R1, R2, and the precoding and decoding matrices. So let's write it as follows. In this case, maybe I will move my paper a little bit. So let's start with the transmitted signals. S1. And maybe I will listen to you. So S1 of size, and maybe, of course, let me show this information here. So what is the size of the transmitted signal to user 1 in this case? So it is vector. Oh, yes, R1, but what the main constraints for R? So we can say that RK should be less or equal to MRK. You can also see it in the multi-user Mimo, what is paragraph. So what is the size of the S1? Because maybe you will have something like this on the exam. So you can see the number of receive antennas here. and I think you can say the size of this vector in this case. Oh, yes, it is just 2 times 1. So 2 rows, 1 column. Then second transmitted signal to the second user. Yes, because the number of receive antennas for user 2 also 2. So 2 times 1. Then the size of received symbols for the first user. So it is equal in this case MRK. And you can see also is the same to 2 times 1. And for the second user, it is also 2 times 1. Then the precoding matrix F1. So you can see it should be equal to MT times the rank of the first user. Yes, 4 by 2. Because the number of transmit antennas at the base station is 4, and the number of receive antennas is 2. And for the second user, yes, it is the same, 4 times 2. And the last thing here is the decoding matrix, D1 and D2. So what you can say about these matrices, of which size it should be, or they should be? Not 2 by 4. Yes, because here the number of receive antennas, you can see. So in this case, it is 2 by 2 and 2 by 2. So let me check. I think I also have the small. So we will end. We'll continue this task, but also I have one short task for such multi-user Mimo. So the next subtask here is theoretical one. So B, in order to perform, maybe let's write it. In order to perform this precoding matrix at the transmitter, in order to perform this FK at the base station, does the transmitter requires channel state information? So does the, in this case, base station requires channel state information? So what you can say, what is the answer to this question? So also you can use, of course, your notebooks. So first thing here, what is the precoding at the transmitter? So we can go through our lectures and we can say that we use a matrix with this FK, but this FK calculated using zero forcing. Then we can say, for example, so this zero forcing is pseudo inverse of a channel. What is next? Pum pum pum, etc. 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 And as the end of all calculations, we can say that f for user k is equal to the matrix V for user k. But we calculate this V using singular value decomposition of the channel. So does the base station requires this channel state information? Yep. So the short answer here, yes. But also here one more question. How can channel state information be obtained at the transmitter side? So how can channel state information be obtained at the base station? At the base station. As I remember, we have another lecture, but I think somewhere in the beginning, or not in the beginning, in the middle of our lectures, when we introduce time duplex and frequency duplex. As I remember, but I don't remember in which lecture this thing was. Maybe it is lecture 5 or 6. Yes, lecture 5. You can open lecture 5, and here you can find this time division duplex and frequency division duplex. So let's read these two cases together. So time division duplex, we send pilots on the uplink. In the frequency division duplex, we send pilots on the downlink. Then we can see that channel state information feedback from the UTs or user transmitters to the base station. So yes, the main answer is in the lecture 5 in clause with this frequency division duplex. So
завтра есть английский? Завтра 15. We start and see lecture at 1:30 tomorrow, okay? 1:30. Okay.
Maybe you can also, yes, are you here? Yes, Ruslan?
Yes, we're here.
So Artur Kamilovich said that your IMCN lectures or practices will start at the 1:30 tomorrow. Okay?
Okay, good, yeah.
Right. So the short answer here, yes. And you can write it like, we need this information to calculate something like singular value decomposition, to use it for zero forcing, etc., etc., etc. And answer for the second question, we can use this frequency division duplex and send pilots on the downlink, and as the feedback from mobile users, we will have this channel state information. So I will write only short answer, yes, and we should use frequency division duplex, FDD, to obtain the channel state information at the base station. Okay. Here, next subtask is we should provide an explicit expression of a received signal R1 and R2 for channels for users 1 and 2, of course. And let's write this one here. So C1. So we should provide an explicit expression for R1 and R2. I think I have something here also for this case. So maybe let's start with a general equation for just one user, Mimo, to see how we can get these explicit expressions for user 1 and 2. So the general equation is y. Maybe we will leave this scale factor here and just write our channel times transmitted data plus noise, like this one. So in this case, we can say that our channel H is equal to H1 concatenated with H2. So first thing is this part. Next, we can rewrite our transmitted data S. So this transmitted data S, for example, let's write S1. We can say that we use precoding scheme here. And precoding thing here is this matrix V1, as I remember. Let's check it here. Yes, so F1 is equal to V1. And maybe we can say that this V1 is calculated from this thing here, is calculated from singular value decomposition of H1 times P1, and this P1 also calculated from the singular value decomposition of H1 tilde. So SVD of H1 tilde, which is equal in this case to H2. You can see we need to write this H1 tilde without our channel H1, so it is just H2. And here our transmitted data, let's maybe use D in this case, so some transmitted data 1. So it is the transmitted data for the first user, and then we can write the same thing but for the second user. So S2 is equal to V2 recording matrix times some transmitted data for user 2. Okay. And in this case, let's write our receive signal for user 1. Of course, I think we should start with decoding matrix. So first one, we multiply this thing with decoding matrix. We can call it as D1. And next, we should write what we receive from the base station. So it will be something like H1, H2. So it will be something like channel 1 multiplied by this transmitted data to the first user, plus through this channel 1, we also will get the interference from the second user. So it will be also the same H1, but with this pre-coding matrix for second user times transmitted data for second user. And of course, here we receive some noises for first user. So it is something like plus vector n1. And maybe next I will rewrite D1 using U1 Hermitian. But of course, we can write instead of V1 and V2, F1 and F2, if you want. So next, we write U1 Hermitian times H1 times V1 times our transmitted data plus the same equalization or decoding matrix multiplied by the same channel, but in this case with the transmitted signal to the second user with its pre-coding matrix. And plus, oh, sorry. U1 Hermitian multiplied by the noise. So we provide the explicit expression for the first user, and here we can show three different parts: the desired signal, the interference, and the noise. So we can say that this one is the desired signal for user one, desired signal. This thing, in this case from user 2, is interference. And this part is our noise for our first user. And of course, for example, if in exam we say to you that you should provide an explicit expression, you can write it as follows, just one line expression. So without these big things here. But if you want to write this thing, you can also write the overall notation thing and etc. But if you write only this expression, or if you use the general notation for precoding and decoding as D1 times H1 times F1 times, for example, let's write it as S1, then multiply D1 H1 with precoding for the second user, with transmitted signal for second user, and plus the noise. So it is also a correct version of the explicit expression. So you can write it as this one or as this one. It is also correct things. But here, in addition, you should denote the parts with the desired signal, interference, and the noise. And let's use maybe using this expression, general one, for the second user. So received signal for the second user. We can use this thing, and we can say that we have first decoding matrix times channel for user 2. Then let's maybe write first user. So precoding matrix for the first user and transmitted signal for the first user, plus decoding matrix second user, channel matrix second user, precoding matrix for the second user, and transmitted symbols for second user, plus the last thing with noise, decoding matrix and the noise. And we should denote here that this one, in this case, is the interference from the first user. Interference. This one is the desired signal. Desired signal. And the last thing here is the noise. We can use D2 matrices D and F, or also we can use U and V. So it is the same thing. No, yes, for the second user, we have second channel. So channel for second user, because here we use channel for first user. And maybe let's make short break, something like 10 minutes, and we will continue at 16:45. First, I will give you also multi-user Mimo, but we will calculate projection matrices. So we will have some numerical values here. And also I will introduce to you homework number 2, and maybe we will start it together today. So I will give you some main ideas what you should do, and maybe I will show you some Scratch, how you can do it in MATLAB. And then we will continue in the next week. So we have today 1 practice and 3 practices next week. And 1 week after, if you want, we also can make some meeting to discuss some questions if you have about lectures, about practices, or whatever. So yes, let's make short break right now. Tak.
Не знаю, как это, как именно шаг сделать, какой шаг. Где просто минуту нравится менять эту тему. Сейчас делаем, когда началась, начинаем переключать. Интернет цепи. Онлайн звук. Я что включено? Ну вот один это типа был первый сигнал. Вот это вот нет, не понял, я спрашиваю про буквы. Вот видишь, вот тему, да. Д, это понятно, вот написано H, вот. H остается. вместо F1 должно поставиться F1. Не понимаю. Окей, смотри, вот S1 это V1, D1, а F тогда что? Его вообще нет. Это получается одна из версий вот этого.
Да, это прям как общая формула, так сказать.
Да, вот смотри, вот D1, вот мы изменяем на улучшение,
Да.
получается.
Да.
H1 оставляем, да.
Да.
Потом S1 мы заменяем
Но
на
это я написал так, чтобы не было так, что типа S1 равно V1 равно типа умножаем на S1. Ну, было сравнивать то, что типа S1 равно что-то и умножим на то же самое S1. Я, вот, чтобы просто не запутаться, написал V1.
Просто я не понимаю, вот куда тогда F чему равно. Раз остается эта вот часть. S. То есть, как бы, F пропал просто.
Ну, тут, наверное, правильнее будет сказать то, что, ну, вот, здесь мы D1 заменяем на S1, как и должно быть, а V1 заменяем на F1. То есть, вот, да, немного...
То есть в этой
путаница
части
получается.
это и есть F.
Да, так есть. Я просто, да, не нашел лучшего варианта написать с заменой. Но проще, наверное, будет показать вот в общей форме.
Хорошо, понятно.
То есть, потому что там изначально вам дано только вот, ну вот то, что я вам показал, даны S1, S2, R1, R2, D1, D2, F1, F2. И то они только вот в буквенной форме, без чисел, без ничего. В чистом виде.
Let's maybe start MATLAB. MATLAB.
Если бы там сказали, давай, нет, 50%. А пришел с пустыми руками, начал с портфелем. С пакетом. Я закончу. Записав на руховье пакет, бумага такой. квадратного метра. Да, на квадратном метре я не делаю. До 12 килограмм квадратного. Зарплаты 70. Это у кого? Логично, можно. Собственно, это
Окей.
построил график.
So first, let me show you one more task, but a little bit easy task for multi-user Mimo with numbers. So here we will have also two mobile users, but first one will have only one antenna and second one two antenna. So in base station, we will assume that we have 3 antennas. So let's write task 4 in this case. So short example of multi-user Mimo with some numerical things here. So task 4. We assume also multi-user Mimo. At the base station, we have number of transmit antennas equal to 3. For mobile users, first one, MR1 is equal to 1, and MR2 for second user is equal to 2. And maybe we can show it with small figure here. Let's assume our base station. It has 3 antennas. And from right side, one antenna for user 1, or I will write user equipment 1, and 2 antennas for user equipment 2. Something like this. Next, we have an information about channels for this user 1 and user 2, and also we have an information of the singular value decomposition of these channels. So let's write channel 1. In this case, it is only the column vector because we have only one antenna, but not the column, the row vector. So H1 is equal to 3, 0, and 3. And also we are given by the singular value decomposition. So it is 1 times, here we have 3 times square root of 2, 0 and 0. And the last thing here, the right unitary matrix. So it is of size 3 times 3. First value, maybe let move 1 divided by the square root of 2 outside. So this matrix is 1 divided by square root of 2 times, here first one it's 1, then 0, 1. Second row it is 0 square root of 2, 0. And the last one it is minus 1, 0, and 1. So if we multiply this one by the 1 divided by the square root of 2, it is here, 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 here. We will have 1 divided by square root of 2, and in the index to 2, we will have just 1. Something like this. So channel 2. So it is channel for second user. First row it is 2, 0, 0, and second row it is 0, 1, 0. And here, left unitary matrix, then right, then singular value decomposition or singular value matrix. And the last thing is right unitary matrix, which is also identity matrix of size 3. So let's assume that our first subtask, it is a calculation of a projection matrix, or maybe let's first, okay, I will write it as follows. For example, let's say that subtask A is how we can show channel with tilde for first user and second user. So we need to write what we have for this HK with tilde, where K goes from 1 to 2. So if you assume user number 1, H tilde 1. What we have in this case? So we need to create the matrix without the first channel. So what is it? Maybe I can show you what we have overall. So overall channel is H1 concatenated by H2. So what we have if we want to write H1 tilde? Huh? Yes, so it is just channel 2 of user 2. So H1 tilde is equal to H2, and we can say that this H2 or this thing, if we write the singular value decomposition, is equal to U1 with tilde times sigma 1 with tilde times V1 with tilde Hermitian. But you can see already that this U1 with tilde, sigma 1 with tilde, and V1 with tilde is the same to this one. So U2, sigma 2, and V2. So we can write it as U2 times sigma 2 times V2 Hermitian. So next, for user 2, we also want to create this H with tilde but with index 2. So matrix H2 with tilde. And in this case, what we have? So we need to remove this one, H2. And it is equal to just the channel of the first user. And also we can write here that this thing is equal to U2 with tilde times sigma 2 with tilde times V2 with tilde Hermitian. But it is also equal to matrix U1, but maybe I will show it as scalar here. So U1 times our sigma, or maybe let's use matrix notation. So to keep the same style. So next, let's calculate the projection matrices for this first user and second user. So B, we need to calculate matrix, projection matrix. So P with index K, and also K goes from 1 to 2. And let's check our notes. So what we have here about P1. So you can see,
Maybe I will open it here. Which is the last lecture number 12.
So first we create this channel H1 with tilde, for example, for user 1. Then we calculate the singular value decomposition, but we already got this singular value decomposition, which is equal to the singular value decomposition of the second channel. Then we should take the null space, you can see. So let's write user1. We have this channel h1 with tilde, which is equal to u2 times sigma 2 times v2. To calculate the projection matrix, we need to get the null space of this matrix v2. And maybe let's see it in the beginning. So you can see for the second channel, we have rank 2. In this case, we can say that first and second column is our signal space. So we can divide it as follows. So this part is the signal space or signal subspace, and this one is null space or also null subspace. So we need to take this null space first and multiply it is as follows. So let's write maybe a general equation first. So this P1 is equal to V1 with tilde, the null space, times V1 with tilde null space Hermitian. But of course, we can write it as V2 null space times V2 null space Hermitian. So in this case, V2, it is column vector with values 0, 0, 1. So this one, because it is already the Hermitian version, but we need without Hermitian first. So first one, it is 0, 0, 1. And we multiply it by the 0, 0, 1. So it is matrix multiplication, and we will have a matrix of size 3 by 3. And all values are equal to 0, but the last one here is equal to 1. Yes. And this one is the projection matrix for user 1. Next, let's do the same thing for user 2. I will take now a picture. So user 2. In this case, the projection matrix 2 is equal to V2 tilde null space times V2 with tilde null space Hermitian. But of course, we already see it that this one is equal to V1 null space times V1 null space Hermitian. And let's check what we have in this case for matrices V1. So do you see it? Yes, but also we need to take something more. Yes, but more. You can see, yes, because you can see that here we have only rank equals 1. So what means that first column, first row, it is single space, and overall this thing, and also multiplied by the scale factor here, is equal to null space. So this one is null space. So now we can write. I will move both scale factors to the left. So we have here 1 divided by square root of 2 times 1 divided by square root of 2, then multiply it by the first row, but in column version. So 0, square root of 2, 0, and second one, it is -1, 0, and 1. Then we multiply it by 0, square root of 2, 0, and -1, 0, 1. So we will have here 1 divided by 2 overall. And what we have for these matrices. So I can say that it is of size 3 by 3 also. So we can make here 3 by 3 matrix. And what we have, 0 times 0, then plus -1 times -1, each is 1. Second one, it is 0 times this square root of 2, and 0 times -1, so it is just 0. And the last thing, 0, 0, -1 times 1. This one is -1. Here 0, so it is 0 thing. This thing give us 2. Oh. And the last thing here is also 0. And for the third row, 0 times 0, 1 times -1, -1. 0, 0, it is 0. And last element is 1. So we calculate the projection matrix for Z2. But remember about this scale factor, because sometimes it is given inside of this matrix. Sometimes it is given as outside scale factor. So what is next we can do here? Let's maybe we calculate projection matrix. And maybe we can see what we have if we multiply our channel by this projection matrix, for example. Let's check this one. And the last thing, we will talk about the precoding and decoding matrices. So next, projection matrix into the null space of H1 and H1 and H2. Yep. So let's assume this, for example, subtask C. Let's assume this multiplication of channel K times its projection matrix, also P with index K. And K goes from 1 to 2. So for user 1, it is H1 times E1. and we can see, let me check it. Okay. Okay. Okay, let's write this thing here. So first one is 1. Then we will let's move outside this square root of 2 from here, and we will have just 3. I think it is a good point here. So let's move this square root of 2 times 3, 0, 0. Then multiply this thing by 1 divided by square root of 2. Multiply overall thing to what we have here. 1, 0, 1, 0, square root of 2, 0, minus 1, 0, and 1. So this thing we multiply by this matrix of zeros, and last element is equal to 1. So zeros. And last element is 1. So we can see these scale factors here is eliminated or give us 1. And what we see by this multiplication, so we will have 1, 3, 0, 0, and here 0, 0, 1. So 0, 0, 1. Then 0, 0, 0. And this thing is also 0, 0, 1. If I'm not mistaken. 1, 0. But maybe I'm mistaken. So okay, let's continue. And for channel 2, I will give you the answer. Maybe I'm mistaken in case that I think this multiplication will be given to you, because I don't have the task for it, but I have the solution for this task. So let me write. So they write this thing as square root of 2, 0, 0, 0, 1, 0. And the last element here, 1 divided by square root of 2, 0, minus 1 divided by square root of 2. Here, 0, 1, 0. And the last thing here, 1 divided by square root of 2, 0, and 1 divided by square root of 2. Maybe I will recalculate this thing also for our task and show you in the next lecture on Monday. So the main thing here is the precoding matrix and decoding matrix. So what we have?
Excuse me.
Yes.
What does the projection matrix tell us?
Yes, you can see it next from our lectures, yes, and I will say you next this thing. So you can see that first we multiply H1 by P1 if you check our lectures and calculate the singular value decomposition. So H1 times P1. We calculate the singular value decomposition, so we have this singular value decomposition here. And from this singular value decomposition, we get the precoding matrix and decoding matrix.
So we use it for the precoding.
Yes, and for decoding. So you can check it also from your notebook. So the main thing here that we need to use the economy size. So we use economy size. Yes, we can. In this case, let's write maybe it as subtask D. And we want to get the precoding matrices and decoding matrices for K1, 2. So first, we assume user 1. And let's work together. So if you open your textbook, you can see that F1 should be equal to V1. And in this case, the rank of this first matrix is equal to 1. And we can say that this thing is our precoding, because this thing is maybe let me write it here. This thing is V1 Hermitian, and this one is V1 Hermitian. And if we assume this general case for Fk, Fk is equal to Vk. Let's write as single subspace. In this case, our rank is equal to 1. We have this first row, but we should write it as column. So for user 1, we have, let's maybe move this one, F1 is equal to 0, 0, 1. And it is very interesting next. So if you check also our notebook, dk is equal to uk. Let's write also with this signal subspace thing, Hermitian. So what we have for first user in this case? So D1. Can you see it? So we somehow should get it from channel H1 times projection matrix P1. Do you have any ideas? One more time.
какие-то одно сигнал space.
Yes.
А почему мы берем это из вот этого процесса, который выделяется с самого начала?
Because it is from our lectures. You can see that here we calculate first h1 times p1, calculate the singular value decomposition, yes, and from this thing we get this f1 and d1. And in this case, d1 is equal to u1, but u1 is equal to yes, it is just one value. Oh. So we can say that d1 is equal to 1. Because this thing here is our u1. And also I can say that it is u1 of signal space because it is only one thing. So this one u1 signal space, and also this thing is v1 signal space Hermitian. First column. And let's write same thing for user 2, and then we will see the homework number 2. So user 2. So F2 should be equal to V2. And in this case, you can see that we have rank equal to 2 from this part. This one and this one. So rank is equal to 2. So we need to take first 2 rows of this singular value decomposition. Because this thing here is V2 Hermitian, and this part is V2 signal space Hermitian. So we need to write it without Hermitian. And first column is 1 divided by square root of 2, 0 minus 1 divided by square root of 2. And second column is 0, 1, 0. And next, decoding matrix is equal to signal space over left unitary matrix. But you can see we already have full matrix, this one. So it is U2, or also it is equal to U2 signal subspace. And of course, we need to take the Hermitian of it, but the Hermitian of the identity matrix, it is same identity matrix. So 1, 0, 0, 1. In this case, it is the same sizes because we assume that we have the full rank. But for example, if we have a mobile station with 2 antennas, but we transmit only one data stream to it, we will have something, some value here, and this one will be equal to 0, for example. Or maybe it is not 0, but we should only take the first part in this case. Like in this case, it is, let me see. So we divide it as this one, for example. And this one will be the signal subspace over U. and this one will be the null space of the U. Because it can be something like unitary matrix, but we need to see it through the singular values. Because, for example, if we have here 0, we can say that we have only one data stream in this case. Yes. So let's move to the MATLAB. And first, I will introduce you the homework, and we will read it together. So what we should to do in this homework, we will see. So I hope you can see clearly this homework. In this homework, we can see the two-channel realizations, but I think we already write these two channels in task 1. And maybe I will change the values inside of this matrix, but maybe something like just 1, 1, 1, 1, 1, here -1, and here will be the full row of 1s. So in this case, you should, as an example of task 1, you should calculate it arithmetically, so without MATLAB. You can do it maybe in white papers, and then take a photo or take a scan and add it in PDF as photo, for example. So first you calculate the eigenvalues. So for eigenvalues, we can use so in task 1, we already have eigenvalues. No, we also calculate these eigenvalues here. So you remember, to calculate the eigenvalues, we just need to solve this equation. So the determinant of A minus lambda times identity matrix, which should be equal to 0. And also this equation is given in hints, and we also will see the hints. So first calculate the eigenvalues, then also arithmetically calculate the open loop. Then we should find this optimal power distribution, and as the last step, we calculate the closed loop capacity. It is the first part of this homework, where you should calculate everything by your hand. And next thing, we work in MATLAB. And here, in the subtask 2.1, you should write a MATLAB script to generate first this HW. So I will show you how you can do it. And we need to write the script, which will calculate, let me check, the ergodic capacity here. We assume that channel is unknown. And for this ergodic capacity, we should average the results over the at least 1,000 realizations. Then we use this written MATLAB script in second task. And here we will change the signal to noise ratio. So we change So we choose 0 to 4, 6, 8, 10 dB, and for each signal to noise value, we create at least 1000 realization, calculate this capacity, average it, and after that plot the result. So this one is second, and here the biggest one, it is 2.3, because we assume different cases. So here we have channel model as given by the sum of line of sight and non-line of sight. So this thing was used in the first homework. And here you can see, first we assume that we have no correlation at the receiver, but we have correlation at the receiver, but the transmitter have no correlation. And we assume the case without line of sight. Then we change the cases that transmitter have some correlation, the same correlation metrics, but the receiver has no correlation. Then we assume both sides have correlation, and also these cases without line of sight. And the last thing here is to calculate this uncorrelated channel. And maybe it will be good not to plot like pictures for each subtask, but you can plot it together A, B, C, and D as one plot. So it is non-line of sight cases. Then here also 3 line of sight cases. So you can see we have no correlation, and the channels are the same. Then we change the channels, but we have no correlation here. And also you can see we add this line of sight. So the racing factor in this case is equal to 20. And the last thing, what if we have identical channels, but correlation at the receiver? And also for this E, F, and G, I think you can plot one overall plot with all these 3 cases. The same thing we do for A to G, but when we know information about channel at the transmitter. So it is something like butter pouring algorithm. So how we can get knowledge about the channel, but not how to get it, how to improve our capacity with this knowledge about channel. And the last thing here, how the capacity is changed if we change the number of receive and transmit antennas. So first case, it is MRMT equal to 2, then MRMT equal to 4, and MRMT equal to 8. And here you are given by hints. So first one, it is for how we can find eigenvalues. Then main equations for open loop capacity and closed loop capacity. And here information that if we create randomly drawn complex Gaussian channel, this HW, we can use random with normal distribution plus this random with normal distribution times 1J. And in this case, you will have a variance equal to not 1, but something like 2 approximately, or square root of 2. And from one side, you can divide it by square root of 2, but also I will show you how we can do it in our way. And here are some additional things that you should remember about trace and how we can calculate signal to noise ratio, because in the beginning, you are given only by the power, which is equal to 1. I think somewhere here, yes, the power equal to 1, and the signal to noise ratio is equal to 1 divided by this variance. So let's start from the beginning with this MATLAB script. So first we need to create our channel. So let's see. Maybe I will leave this part as this thing. Let's create another script, and we will write it as function. Oh, what caps lock? Function. So as output, we want to get specially white channel, HW, and let's call it as generate channel, for example, channel. So as input, what we need to have, or let's check it one more time, what we want to get here. Given the frequency, write a MATLAB script to calculate the ergodic capacity in this case. But first we need to create this HW. Let's maybe generate channel. And here we need to add information about number of receive antennas, number of transmit antennas. And that's all, I think. So we can here. And HW, it is just random with normal distribution. First, number of receive antennas. Second, number of transmit antennas. Then plus 1 times J, random, normal distribution, MR, MT, and closed. So let's save this as generate white channel. And if you use it here, let's call it HW, generate white channel. And let's assume that the number of receive and transmit antennas is equal to 2. Let's check this code. So yes, we have this HW. Next, let's calculate the variance of this HW. Variance of HW is equal to this one. And you can see we have 2 variances for the first and second columns. And you can see it is equal to 0.6 and 10. So it is not a unit variance for this channel HW. So how we can do it in proper way? I think, let's check it HW, for example, let's call it just normalized, for example, and we will calculate it as follows. So HW divided by the square root, but not of 2, but square root of the variance of this channel W. And let's check our variance, HW normalized. Variance of HW so let's calculate this thing, and we have some problems, I think, here, because maybe this one. No. Huh? Ah, yes, thank you. Let's check it. So you Yes, we need to divide it by element wise, I think. No. So what we can do here, because if we divide it like this one, we'll have a matrix of size 2 by 1. It's not right in this case. Oh,
Multiply by 1 over square root of it.
like maybe like through the for loop, or
No, it's 1 over square root of variance multiplied by
let's try like this one and times this one.
then the bracket for the first.
Okay, let's try. So we will put this thing into the braces. No, because I think we can write this. Let's maybe write it as for loop in what we need to do here. So for init column from 1 up to 2 in this case, let maybe try to do it like this one. So we save all rows for init column, and it is equal to the all rows init column here. We divide it by the square root of the variance of this column. Let's maybe do it in this way. And of course, for example, we can create HW norm as the zeros of size HW. Yeah, great. And you can see in this case the variance of our normalized vector is equal to 1 and 1. So let's add this part here. So we can say that we need to go for MR init column for empty in this case, and this HW init column, the same column, divided by the square root of the variance of this column. And now we can save this one, so it's already normalized, and check it here. So yeah, this one saved, this one also saved. Yes, great. So you have this white channel. Next, we need to calculate, not calculate, but write MATLAB script to calculate the ergodic capacity. And we should average our results over at least 1,000 realization. So let's check how we can calculate the open loop capacity. So here we can see that we need to calculate the eigenvalue decomposition. Also, we need to add an information about transmit power, noise power, and this one is given by empty. So let's write function calculate capacity. Here, what we get, let's maybe call it as ergodic capacity, or maybe C ergodic. Inside of this function, we should send the number of transmit antennas, our transmit power, then sigma n, and yes, that's all. So what we should do here? First, maybe we can add here the number of receive antennas also, MR MT. Here we will create our channel first. So let's add an information here. Create white channel. And in this case, we use HW, which is equal to generate white channel. So MR empty. Then we need to calculate the eigenvalue decomposition. Compute EVD of HW. So let's check the documentation. EVD. Will be as just EVD. Or we can, let's write eigenvalue. Okay, in this case, we can use singular value decomposition. So HVD. And if we write it as one symbol, we will get singular values. Okay, so we can say that S, matrix S, is equal to the singular value decomposition of our channel. And then we recalculate it to the, let's call it lambda. Lambda is equal to just S in the power of 2. Great. And next, let's calculate the capacity. So in this case, we just need to sum over our value R, the logarithm base 2. So how we can do it? Maybe if we use sum. Okay, maybe let's write it as follows using the for loop. Just for loop. The rank. We should maybe no rank is equal to value of MRMT. But for our case, it should be equal to 2, I think. So init, how to call it? let's call it maybe I, just I, because we go for this I. So I goes from 1 up to channel rank. And we need to first create C ergodic as 0 value. Then C ergodic plus list 2, I think like this one here. We should use it. Yes, logarithm base 2. Instead of this logarithm, we have 1 plus p divided by mt times sigma n, and multiply it by lambda. With values I and I think. So let's check this part of the code. Maybe we can. Okay, let's see this one. So let's try to use calc capacity. So C ergodic is equal to calculate the capacity. First, we should write MR in T. So let's write 2 and 2. Let's say our P is equal to 1. And sigma, and let's maybe also equal to 1. Ah. Error in line 3, somewhere here. Up. Thank you. Yes, here we have it. Let's check it one more time. What we have also the power. Yes, of course, because we have the matrix here. So we use it with dot and the power thing here. Okay, so maybe we can check it with this breaker here. And let's see what we have. So we create C ergodic, lambda is equal to, okay. So yes, I see that we should use just I in this case, without second I, like this one. Yes, of course. Remove this breaker here. Yep. So we get this C ergodic, but we need to calculate it for iterations. Yes. So let's add here also the number of iterations. Number of iter number. Let's write this. Then we should create different white channels, I think, here, because we need to compare it like for different, especially white channels. So here, let's add here for example, init iteration, which goes from 1 up to number of iterations. you can put here end, and as I remember, you can use Ctrl-I, yes, to get the proper proper spacing. In this case, we should remember that our C ergodic in this case changes by these iterations. So let's create another value here. Let's call it as maybe C ergodic overall. Zeros of size, for example, let's put it as column. So number of iterations. Right, create the maybe subspace, for overall ergodic capacity. And you can see that we put this channel rank inside of this thing, so we can move it outside, yes. And maybe let's call it and the minimum dimension. Or find the, let's call it the channel rank. So channel rank here, C ergodic here, but also we should save this value. So we should add C ergodic overall here and put for this init iteration. Yes, init iteration. We save this. So maybe let's check one more time this code, and let's put, for example, 100 values here. And one thing what I should add here, that we change the output of this function. Yes, you can see we have 100 value, but we should calculate the overall. So let's, yes, change this C ergodic overall as, I think we can use the mean value because it is the summation of all values and dividing it by the number of it. So, but maybe check it because it is really interesting case. So what if, let's calculate of C ergodic, and let's calculate it by our hand. So it is the summation. So like average C. So we divide it by 100 and multiply this thing by the sum of overall C ergodic. And what we will have in this case. Yes, so we can just use the mean of C ergodic. Great. So let's put here C ergodic. Maybe ergodic averaged mean of our C ergodic overall. Maybe it's better. Okay, let's use like this one. So now you can say that you already have done this first part of the homework. So this one. Maybe let me show you what we should do next. For example, so we use this program, but we add this signal to noise ratio value. So let's maybe, you can see that we have these values MR and T. So it is something like parameters. For example, number of receive antennas is equal to 2. Number of transmit antennas is equal to 2. Then what we have, number in the power, and the number of iterations. We have, for example, 100. So next, we create the signal to noise ratio vector, which is equal to, for us, it is from 0 to 10 with step it in this way. Let me check. Yes. And we need to calculate using this signal to noise ratio the different ergodic capacities. So for init, for example, SNR, which goes from 1 up to the length of this signal to noise ratio vector, we will calculate this ergodic, but with number of receive antennas, number of transmit antennas, the power. Then we should recalculate sigma n, and here number of iterations. So we calculate sigma n in hints you are given by the equation. So let's check it. So yes, this one. So this sigma n is equal to 10 in the power of minus signal to noise ratio divided by 10. We can write 10 in the power of minus, and also let's use SNR as SNR vector with init SNR. So we first take the value of a signal to noise ratio, put it divided by 10, and put this sigma n inside of this thing. And also we need to change this C ergodic by this length of the signal to noise ratio. So we should create outside of this loop the subspace. Maybe let's use length, or maybe we can use it as size. Let's add maybe some information here. This one is number of receive antennas. This one is number of transmit. The transmit power. This one, number of iterations. And here, first we create the vector of signal to noise ratio values, for example. And here, create the subspace for ergodic capacity. So first we take init noise ratio. Then calculate the variance of the noise, and then let's compute the big capacity for init. Let's check our code. Yeah, great. So this one, something like the second part of your homework. And here, let's, for example, see what we have in this case. So first, we should write the vector of signal to noise ratio, and then the ergodic capacity vector. And you can see, if we increase, maybe that's bad, that our X label, what we have, signal to noise ratio in decibels. In Y label, we have, let's call it ergodic capacity. And okay. And you can see, if we increase the signal to noise ratio, the ergodic capacity also will be increased. So from this plot, for example. And maybe I will show you the last thing here. What we should do next. You can see we will use this value here. So I recommend you to write the function to compute this type of the channel. So something like function, for example, channel H, and let's call it generate just the channel. Generate the channel, and you can see you should put here variation factor. You should put here the correlation matrices for transmit and receive antennas. And what is, and yes, that's all. So K, covariance matrices, and maybe this matrix, H line of sight. But for example, let's show K factor, H with index line of sight. Our receive, transmit, yes. And here, you can, if you want, you can add here also a number of receive antennas and number of transmit antennas. But for example, you can get it from the size of the receive antenna, and the same thing for the transmit antenna, for example. This one. So next you should create this HW, so we can use generate channel with with more MT. Yes, yes. R. Next, you should write this equation like this thing, SQRT of k divided by k plus 1 times this h line of sight plus what we have next, SQRT of 1 divided by k plus 1. We multiply, yes, in this case you should, yes, you can use SQRTM, but if you want, you can also write your function to calculate this square root function, square root matrix. So SQRTM, R, then our channel HW, and then SQRTM of RT. Something like this. So, and also with permission. So it will be good for you because you will reuse this function, because you can see you have 1, 2, 3, 4, 5, 6, 7 different cases with different values, and also you will have same 7 cases for closed loop capacity. And also for this closed loop capacity, you should write the butter pouring algorithm. Then, so you can calculate it using EVD if you have this library, but I think we have no this library here. Of course, you just can use SVD, take the, yes, the square of it, some butter pouring algorithm scheme, so it is iterative thing. Then if you see negative value, you switch it off one more time, check it, and if you see that all values are greater than 0 or equal, you can break this this function. And yes, so you need to write approximately 3 if we assume this one. So this one first function, this butter pouring algorithm second function, and a function for this calculating of ergodic capacity. But of course, if you want, you can add additional functions for you to get maybe better look of your code if you want. And as I said before, it will be good if you plot A and D in one plot or in one figure, E and J two in our figure. And for 2.4 also A and D one figure, E and J in our figure. And this thing is the same, so you just use especially white channel, change the signal to noise ratio, and assume 3 different cases. So I will one more time check this document to the typos, and I will send it to you. And maybe I think it's enough 1 week for it. So maybe let's June 9th. So approximately exactly 1 week. So I will send today, but you will have so the last day is 9th, because you will start from tomorrow maybe. So yeah, I think that's all for today. If you have some questions about homework or about tasks in practice or about the lectures, of course you can ask me. And I wish you a nice evening today. So feel this summer weather. So yes, Ruslan, goodbye.